The next generation of space telescopes will allow us to identify the first habitable exoplanets. They'll do this by dissecting the light reflecting off these planets to determine the compositions of their atmospheres. But resolving the surfaces of these planets requires a telescope far more powerful than anything we can hope to build in the foreseeable future. However, nature gives us a way to use the sun as a gravitational lens to magnify a distant exoplanet by a factor of 100 billion. That's enough to let us map its continents and oceans and even search for signs of life. It sounds like science fiction, but scientists and engineers are working right now to create such an image within our lifetimes. Welcome back to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer. In our previous video on future space telescopes, we talked about how the proposed HabEx and LUVOIR observatories will have the ability to directly image Earth-sized exoplanets. These telescopes use coronagraphs and, in at least one case, a star shade to block out the light from the star and reveal the planet, which is 10 billion times fainter. For the first time, we'll be able to map their orbits, monitor seasonal changes in their brightness, and identify the chemical makeup of their atmospheres. But none of these telescopes can actually resolve an exoplanet's surface. Such a feat requires a telescope much larger than anything envisioned. How large? Well, let's consider an exo-Earth 100 light-years away. In order to make a 1-pixel image of the planet's surface, we need a telescope 90 kilometers in diameter. That's large enough to extend from Philly to Atlantic City. It's not impossible, but it'll take a while. Light from the planet's host star will contaminate the image, either directly or by scattering off the dust within its planetary system. The only way to increase the signal-to-noise ratio is to increase the integration time to 100,000 years. That's how long it would take to make a 1-pixel image of the planet. And what we really want to see is something more like this, with a resolution of 1,000 by 1,000 pixels, and to create it within my lifetime. Yours too. This image was composed from 4 months of data from NASA's Terra satellite. At up to 1 kilometer per pixel, we can easily make out continents and oceans. We can see color variations and distinguish deserts from vegetation. Not only is vegetation proof of life on this planet, but if we look closely, we can even see lights on the night side. In other words, proof of advanced life. However, a similar sized image of our example exoplanet requires a telescope 90,000 kilometers in diameter. That's 7 times larger than Earth. Even if the mirror were just a single micron thick, it would have a mass of about 1 trillion kilograms. You can't put it in orbit around Earth because tidal forces would just tear it apart. You'd have to put it into its own orbit around the sun, but then it would become an instant light sail and leave our solar system within a year. Plus, no picture. However, there is a way to image an exoplanet in months to years instead of centuries to millennia. In fact, it's the only way to make such an image. General relativity tells us that matter curves space-time, creating gravity. As light passes through this curvature, its path is deflected. Eventually, light rays passing around a massive object converge at a focus, creating a gravitational lens. If we position ourselves exactly at the focal point and look back toward the lens, we'd see a ring of light surrounding the lensing object called an Einstein ring. We use Einstein rings to probe distant galaxies that are being lensed by foreground galaxies. However, Einstein rings are rare because seeing them requires a chance alignment between the source, the lensing object, and Earth. But if we use the sun as a gravitational lens, we could, in principle, position a telescope at the focus for any target of our choosing. As gravitational lenses go, the sun isn't as handy as, say, a black hole, but it is massive enough to amplify a background source by a factor of 100 billion. That's why a team of scientists and engineers are developing a solar gravitational lens mission. The team is led by Dr. Slava Turishev at NASA's Jet Propulsion Laboratory. Turishev and his teammates have been working on this mission for a few years now, and they've already worked out most of the solutions to some pretty staggering problems. For starters, the SGL's focus is far. It starts at about 550 astronomical units. Remember, Earth is 1 astronomical unit from the Sun. Neptune is 30 AU. The Kuiper belt extends to about 55 AU, and Voyager 1, the most distant human-made object ever created, is currently just shy of 150 AU. By the way, it was launched in 1977. At 550 AU, the SGL focus is well into interstellar space, but there's a plan to get there in just 20 to 30 years after launch. We'll talk more about that in a little bit. But once we do get there, we'll have plenty of time to make observations. And that's because parallel light rays that pass farther away from the Sun aren't bent as strongly as rays passing close to the Sun, so these rays come to focus at greater and greater distances. Instead of a focal point, we get a focal line. And that simplifies things because we won't have to bring the spacecraft to a stop once we reach the focus. Instead, the spacecraft continues to image the exoplanet as it flies along the focal line. And that's just as well because pointing the telescope to a new target isn't going to be very practical. In order to change the telescope's pointing by just 1 degree, a spacecraft at 550 AU would have to move 10 astronomical units in the lateral direction. That's the distance from Earth to Saturn. It's doable, but in practice, such a telescope wouldn't be repointed. So you'd need to select a target planet before setting out for its SGL focal line. But that's what the next generation of space telescopes are for. But the problem that's blindingly obvious is the fact that the Sun is blinding. Even at 550 AU, the Sun is far too bright to image the Einstein ring. It would need to be blocked with either an internal coronagraph or an external starshade. But even then, the Sun's corona still puts out a great deal of light. That means we have to travel beyond 550 AU before we can start making images. But how much further? Ideally, we'd wait until we're far enough away from the Sun that we're only imaging light rays that avoid the corona altogether. But that distance starts at around 2200 AU. A spacecraft traveling 25 AU per year would take 88 years to reach that distance. So, Slava Turishev and his collaborator Victor Toth studied the problem in greater detail. They found that a specialized coronagraph designed by Michael Shao at JPL could block everything from the Sun all the way out to the inner part of the ring. Then, by turning off the pixels outside the ring, they could image the Einstein ring with an integration time of just a few seconds. This approach allows the ring to be imaged starting at about 650 AU. Yes, that's still far, but it's a lot better than 2200 AU. But at that distance, the planet's image is going to be very large. To understand why, let's consider a pinhole camera. Light from a source passes through the pinhole and makes an image on a screen. The farther the light has to travel to form the image, the larger the image gets. At 650 AU, the planet's image is 1.3 kilometers across. Instead of an image forming on the detector would be inside the image. This means an ordinary-sized telescope at the SGL can only image a single pixel of the planet. In this case, a 1-meter sensor images a pixel corresponding to a 10-kilometer patch of the planet's surface. The telescope moves to the next pixel location and then makes another image. This is a technique called rastering. Meanwhile, the planet isn't sitting still for its close-up. It rotates on its axis and orbits its star. But not only is the planet moving, but so is the telescope. Believe it or not, the Sun is not fixed at the center of the solar system. Instead, it moves around the solar system's barycenter as it's tugged back and forth by the planets, particularly Jupiter and Saturn. There are many other motions to consider, but they all add up to a predictable wobble of the telescope. The wobble is slow enough that the spacecraft can use ion microthrusters to generate the necessary sideways velocities to cancel out these motions. With these issues addressed, let's consider what a telescope actually sees from the SGL's focus. The Einstein ring is as thick as its image is wide. In our example, the ring is just 1.3 kilometers thick, therefore this illustration is way out of scale. A 1-meter telescope at the SGL would see a ring of light, but not be able to distinguish the ring's thickness. However, as we saw before, parallel light rays passing farther away from the Sun aren't bent as strongly as rays passing close to the Sun. This means that if we're looking at a point source through a gravitational lens, we will see a bright ring from the rays that are in focus, surrounded by concentric rings from the parallel rays that are out of focus. This results in a blurring effect called spherical aberration. A distant exoplanet is very tiny on the sky, but it's not a point source. Light from different points on the planet form their own Einstein rings, which correspond to different pixels on the image. Thanks to spherical aberration, all of these rings are blurred together. However, we can take advantage of this as we construct an image. As the telescope rasters across the image plane, it views the Einstein ring from a slightly different angle, resulting in a unique mix of light coming from the region of the planet being imaged, plus the blurred light from the rest of the planet. This causes the ring to dim or brighten as the telescope moves from one pixel to the next. As the telescope scans across the focal plane, it builds up a brightness map of the image, one pixel at a time. The result is a blurred image of the planet. However, we don't have to settle for a blurred image either. After all, a blurred image is ultimately caused by light from a particular point scattering into multiple pixels. If the source of the blur is understood well enough, it's possible to reassign that light to their intended pixels and reconstruct the original image. This is a technique called image deconvolution, and it's a pretty standard trick of the astronomical trade. However, deconvolution increases noise at the expense of the signal. That's why the signal-to-noise ratio is so important. There are a couple of ways to increase SNR, such as longer integration times, larger telescope apertures, and increased instrument sensitivity. But the real key to image deconvolution lies in understanding exactly how the telescope blurs the light from a point source. This can be modeled with something called a point spread function. The better the PSF, the better the deconvolution. Slava Toryashev and Viktor Toth developed a PSF of the Sun's gravitational lens and used it to simulate how Earth would appear if it were 100 light-years away and lensed by the Sun. Their simulation described the brightness of each location on the image as measured by a telescope at each pixel. Then they applied deconvolution algorithms over a range of realistic signal-to-noise ratios. They showed that with a high enough SNR, an image can be reconstructed with about 25-kilometer resolution. That's 25 kilometers of exo-real estate 100 light-years away per pixel. Planets that are closer will yield an even higher resolution. With repeated observations over time, preferably with multiple telescopes, regular changes in brightness due to the planet's rotation will be distinguished from irregular changes caused by, say, cloud cover. That means over time, it will become possible to remove the clouds and map the planet's surface. None of this will be easy, but it is possible. In fact, it's very possible. But it's also a gigantic undertaking with a fair amount of risk. That's why the team decided to go small. Rather than a single flagship spacecraft, 100 or 200 smaller spacecraft would be used in a novel string of pearls approach. Each pearl is an array of 10 to 20 telescopes, each 1 or 2 meters in diameter. Pearl groups are launched annually over a 10-year period, adding to the string. So how do they actually get to the SGL? Well, nuclear propulsion would be ideal for this sort of mission. It was first developed in the 1960s under the Nuclear Engine for Rocket Vehicle Application Program, or NERVA. Had it continued, it surely would have been the fastest propulsion system available and would have provided plenty of power for the SGL mission. But it was canceled by the Nixon administration in 1973 as a cost-cutting measure, and this is why we can't have nice things. Perhaps one day NERVA will be reinstated and made ready for an SGL mission. But we're trying to get there within our lifetimes. This is why the spacecraft in each Pearl group will consist of small sats equipped with solar sails. The small sats can either launch together or separately in a series of ride shares aboard commercial launchers. They rendezvous in cislunar space outside the immediate gravity wells of the Earth and Moon. There they'll deploy advanced solar sails called sun vanes. Unlike a traditional solar sail, the vanes can be individually articulated to control the spacecraft's direction. This makes the sun vane highly maneuverable. The spacecraft tack into the sun, accelerating as they spiral in. At the moment of closest approach, the vanes are turned face on to the sun to achieve the maximum solar radiation pressure. The closer the sails can get to the sun, the faster they'll accelerate. But the sails have to withstand the intense radiation as well. Current technology can handle a 10 solar radii approach. That's only one solar radius further than the Parker Solar Probe, which uses a large heat shield as it passes through the sun's corona. However, advanced sails may be able to handle approaches as close as 5 solar radii. Because of the sun vane's maneuverability, the spacecraft can make small, precise adjustments as needed, setting it on course to the SGL. By the time the spacecraft are 5 AU from the sun, they cross Jupiter's orbit just a couple of months after their solar slingshot. At this distance, the vanes are no longer needed. Most of the vanes can be jettisoned to reduce mass, while others could be repurposed as antennae, telescope mirrors, or navigation aids. The smallsats race on at 22 AU per year. They cross Pluto's orbit less than 2 years after launch. Within 2.5 years, they exit the Kuiper Belt. Within 7 years, they smash through Voyager 1's distance record at 150 AU. The smallsats are now in interstellar space. There's nothing out here except for the photons of the Einstein ring 500 AU ahead. They'll navigate using laser beacons from Earth, intra-cluster ranging between satellites, intra-pearl ranging between clusters, and very likely timing signals from pulsars. The smallsats will spend most of the next 20 years of their cruise hibernating. They'll occasionally wake up to transmit health and status information. But they'll have one important task to complete before they reach the SGL. Like a swarm of space Legos, the smallsats use their ion microthrusters to assemble themselves into 10 or 20 telescopes. Each telescope is equipped with a 1 or 2 meter mirror and an internal coronagraph. The mirrors could be made from segments carried aboard some of the smallsats. Alternatively, the remaining sun vanes could be repurposed as crude mirrors, and a smallsat carrying an adaptive optics package would correct for the distorted light. I know all this sounds like science fiction, but all of these technologies are real. Self-assembling spacecraft are currently being studied by the US Space Force. Yes, that's a thing now. DARPA, and are now under development at private companies such as NovaWorks and Arcasys. The sun vane concept was originally developed at Elgard, and a technology demonstration mission is now under development by Explore Incorporated. The goal of this first mission is to reach speeds of 5 to 8 AU per year. That's 2 to 3 times faster than Voyager 1. The autonomous assembly of a reconfigurable space telescope, or ARREST, is a CubeSat mission currently being developed at Caltech. The Deformable Mirror Demonstration Mission, or DEMI, is another CubeSat mission being developed at MIT. Meanwhile, advances in artificial intelligence and machine learning will allow the SGL spacecraft to operate autonomously through all stages of flight. The Parker Solar Probe is already doing this as it navigates around the Sun, which is 8 light minutes away. By the time the spacecraft reach the SGL, the round-trip light travel time will be greater than a week. So the spacecraft will need to collectively handle everything, including navigation, fault management, data transfer, and observation strategy, all autonomously. Upon arriving at the SGL, at least one of the telescopes in a Pearl group uses the Einstein ring of the exoplanet star as a beacon. With the beacon acquired, the other telescopes move laterally to the predicted location of the planet's image, some 5 or 10,000 kilometers away. The first Pearl group to arrive will undoubtedly run into unexpected problems. Perhaps there was a little bit more light contamination than expected. Maybe the planet was just a little bit off from its predicted position, and the telescopes had to reposition themselves to another location. This first Pearl group will learn from the mistakes of their creators and serve as the pathfinder for the Pearls to follow. The Pearls communicate with each other, sharing health and status information, and passing down the lessons learned to the next group. Each Pearl improves upon the work of its predecessor. The string of pearls architecture allows for redundancy, efficient power management, and communications. Multiple telescopes in each pearl means more data can be collected in shorter periods of time. As more data is acquired, the picture literally gets clearer. The pearls can follow the SGL focal line for years at a time, monitoring the exoplanet. It would be like having a virtual orbiter, allowing us to watch the planet go through seasonal changes. Another advantage of this approach is that it's completely agnostic of its target. The Solar Gravitational Lens always starts at 550 AU from the Sun, no matter the distance to the object being lensed or its location in space. With so many smallsats being mass-produced, missions to the SGLs of multiple targets could be launched. SGL missions could image the surfaces of individual stars and other galaxies, create high-resolution images of the first galaxies to form in the early universe, and map out the event horizons of black holes. Closer to home, it could create atlases of habitable planets and possibly their civilizations. Over time, we could use the SGL to write the first edition of Encyclopedia Galactica. Most of the technologies needed have either already been created or are under active development. NASA's Innovative Advanced Concepts Program awarded small grants to the SGL team to develop their initial Phase 1 and 2 studies. In April 2020, NIAC awarded the SGL team a $2 million grant for a 2-year Phase 3 study. This is only the third time a Phase 3 grant has been awarded. It will allow the team to finalize the mission concept, design the technology demonstration mission, and transition from a study to an actual mission proposal. It's quite possible that the first mission to the SGL could be launched by the end of this decade. What if, 35 years from now, the first tentative blurry images of an exoplanet began to trickle back to Earth, and a few years later, enough data had been collected to resolve the planet into a clear picture? Challenging, yes, but it's also a very feasible mission, one that is worthy of a civilization. Just thinking about it and knowing there is real work being done to make this mission a reality gives me hope for the future. But in the meantime, we need to discover candidate habitable exoplanets, and that's why NASA is working with the astronomical community to design 4 new missions that will discover them. I made a video about these new telescopes, so I'll see you over there when we're done here. A huge thank you goes out to Dr. Slava Turishev at JPL for his assistance and his patience in helping me to understand all of this well enough to make this video. There's a lot of details I didn't get to cover, but I've linked to his papers below, so make sure you check them out because they're extremely well detailed. And thanks as always to my Patreon supporters for helping to keep Launchpad Astronomy going. And I'd like to welcome my newest patrons, Vincent L. Cleaver, Brandon Davis, Carlos Gross-Jones, Ryan Suter, and Wouter Westenbrink. And a special thanks to Anna for sponsoring at the intergalactic level, and to Michael Dowling and Stephen J. Morgan at the cosmological levels. If you'd like to help Launchpad Astronomy for the price of a cup of coffee every month, please check out my Patreon page. And if you'd like to join me on this journey through this incredible universe of ours, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay home, stay healthy, and stay curious, my friends.